Hello, everyone. Welcome back to the AAS YouTube channel. And we're going to start off with something new this time. We're going to start off with a Sky and Telescope author series. And I'm super happy to lead this series off with Paul Byrne. Hey, Paul.
Hey, how's it going?
Good. How are you today?
I'm good, thank you very much. I'm enjoying my nice perch here in the Venus atmosphere.
I was going to ask, how's the weather on Venus?
Well, as it turns out, actually, this part of Venus is really nice. It's room temperature. You can have short sleeves. You just don't want to go below the cloud deck because it's a self-cleaning oven down there.
Yeah, it starts getting a little acidic, I hear, too. So where are you at physically?
So I am in Raleigh in North Carolina. I teach at North Carolina State University. I'm working from home right now, as most of us are. But Raleigh, so we've just had a storm, ECAS passes by. We didn't get too badly hit, but we're right in one of the regular tracks for hurricane season. So it's an exciting place to live.
Oh, yeah, because one of the hurricanes is going up the coast right now, the east coast of the U.S. Right. I'm in Phoenix, and we'll be a little bit cooler today. We'll hit about 110, 111F. So we're a little bit lower in that cloud deck on Venus than where you are.
A little bit anyway. Yeah.
Definitely above room temp, so it's all good. So Paul, what do you like to do for research?
So I'm a geologist by training. I'm a practicing professional planetary geologist,
Oh, cool.
but I'm really interested in why planets look the way they do. That's what drives my research. So I have research projects that span literally from Mercury to Pluto and beyond. And if it has a surface that we can look at, we can image, or we can even think about, then it's game. I'm interested in it.
Awesome. So that'll lead us into this really nice Sky and Telescope article that you have. It caught my eye, and I went, oh, this one is very cool. And this one is on the fate of volcanic worlds. So Paul, take us away.
Cool. Okay. Well, what kind of drives this this article is a paper that I published in Nature Astronomy at the end of last year, 2019, in which I took data from all 5 inner solar system worlds, right? So starting from the sun, that's Mercury, Venus, Earth, the Moon, and Mars. And I wanted to compare and contrast their volcanic properties because volcanism is a window into the heart, literally, and figuratively of a planetary body. And I'll talk a bit more about that in a moment, but the reason and the timing for this article stems from the fact that just a few years ago, NASA, for the first time, managed to orbit the planet Mercury with a spacecraft called Messenger. Messenger was a mission that launched in 2004, and it reached Mercury and made orbit of Mercury in 2011. It did a few flybys before then and operated for 4 years. Notionally, was going to be there just for 1 year, 1 Earth year, but managed to get 4 Earth years there. And after that, and even to this day and beyond, we're still thinking about all the data that Messenger told us about Mercury. We had visited Mercury, we being humans, in the 1970s with the Mariner 10 probe. Mariner 10 did 3 flybys of Mercury in 74 and 75. But because of the vagaries of how Mariner's heliocentric or sun-centric orbit worked, it only ever saw about the same side of Mercury each of those 3 times. So after Mariner, although we had a rough idea of what Mercury looked like, we didn't even know what half of the planet looked like. Messenger kind of filled in that knowledge gap, but told us a whole pile more, including information on its volcanic characteristics. And so I took the Messenger data and the data that we have been working on for a while, the global image data, maps, and all kinds of stuff like that, chemical, spectral data. And I basically said, okay, well, now that we know what all of Mercury looks like, and we know that volcanism is operated on Mercury, how is it similar and how is it different to the other 4 inner solar system worlds? And then really that kind of led to the conversation of what are all 5 like? And it's not so much just learning about how are they different, how are they similar. It's what kind of insights can we gain when we compare all of them together. One of the things I mentioned a minute ago that I'm a planetary geologist and I'm interested in what planets look like. One of the things that really drives me is this concept we have called comparative planetology. And the idea of comparative planetology is exactly what it sounds like. We look at things on other worlds and we understand what they might be on the basis of what we see on Earth. And vice versa, right? We look at stuff on other worlds that maybe isn't on Earth anymore because it's been eroded or subducted or lost. And we can kind of gain an insight into what Earth looked like way back when by looking at these ancient preserved planetary surfaces. And we can compare planets with each other. So the idea basically of this article here in Sky and Telescope is that it's a more accessible, less academic way of thinking about what lessons can we learn from comparing and contrasting those 5 worlds. Not just about understanding the worlds themselves, but what are the lessons we can take for a volcanic world in general. That's one of the things that really drives me.
So there is volcanism on all five?
Right.
All the terrestrial planets?
All the terrestrial worlds are volcanic worlds in the sense that they show geological evidence on their surface of volcanism having once taken place. Earth is the only world where we know volcanism is happening today. As we say it, the sea floors are spreading, there's pillow basalts pouring onto the ocean floors, and volcanoes all over the surface, erupting, big ones and small ones. We'll talk about Venus a little bit. There's a lot of circumstantial evidence that Venus may be volcanically active today. That is a big unknown. We don't know definitively, but there's, I think, some good supporting evidence it might be. There's no evidence that recent, meaning in any meaningful human time sense, that volcanism is recent on Mercury, Mars, or the Moon. Although some of the youngest flows on Mars are about 2 million years old. That is young geologically.
Yep.
And if we take the attitude that on Earth, we often can define a volcano as being dormant if it hasn't had a historical eruption, but may be able to erupt in the future. I think we can realistically treat Mars as dormant. It may not be erupting right now, and the likelihood of us seeing an eruption in the foreseeable future with spacecraft is statistically low. I don't think we can rule out the possibility that at some point in the future stuff will make it to the surface again. But we see what's really interesting when we make this comparison is that, yes, they're all volcanic. All five worlds show evidence of volcanism, and I'll talk through what that actually looks like. It's not quite what you might expect in terms of volcanism on Earth. But what we can say, and we kind of knew this for a long time, but now we can definitively and quantitatively say this. Mercury and the Moon are much similar to each other than they are to the other three larger worlds, Mars, Venus, and Earth. And in there, I think, lies the lessons we can take for what we might kind of see, you might expect on volcanic worlds elsewhere, including those in orbit around other stars.
So you mentioned the Messenger spacecraft on Mercury. Did it find any evidence of volcanism?
So what Messenger told us is that Mercury has a huge amount of what we would infer to be volcanic plains on the surface. So there's two principles. So to be clear, we did not see volcanoes erupt during Messenger's time on Mercury, and nor would we have expected it to. We did see some surprising stuff, though. One of the ways in which volcanism is expressed, and we know this from the Moon, and I guess from Earth as well, but certainly from the Moon, is that volcanism can be expressed as these large basaltic plains, right? Stuff that pours out relatively quickly. It's got relatively high temperatures, relatively low viscosity, and it just kind of cascades out over the ground and often fills in pre-existing land. You can see ancient craters that are sort of partially or fully infilled. You embay pre-existing topography, you fill it up, and you kind of level everything off. And often, depending on when this resurfacing, we call this volcanic resurfacing, happens, depending on how much time has elapsed between this new volcanism you put in and the age of the surrounding material, the amount of craters on that volcanic plains material will be much lower, right? Fewer craters indicates usually something is younger, because we assume that the older something is, the more time it's been exposed to potentially being impacted.
So it's kind of like tree rings. It's kind of like tree, right?
Right, exactly,
right?
yes.
You can age date the surface by the number of craters.
That's exactly right, and that's exactly what we do. In fact, a lot of that kind of ties into the work we'll talk about in this article, right? We look at the number of craters, and we have a really good idea as to how old a surface is on the basis of the number of craters for where on the Moon we have samples that we brought back to Earth, and we did radiogenic sampling on, so we have actual absolute dates. We don't have samples from Mars or Mercury or Venus, so we extrapolate and we make a bunch of assumptions, and sometimes we make assumptions on assumptions, but it's the best we have until we have actual age dating for those samples. But we can say something about the approximate timing and stuff, and we can especially say what the relative timing is, right? Like, we see an area that's kind of rugged and then there's some smoother stuff inside of it. There's a good chance that smoother stuff is younger because it seems to be sitting on top, and it's a very common approach we take in geology generally. So what we see on Mercury is about 27% of the surface is covered by this smooth stuff. And what Messenger really told us is that it's probably not just that 27%. Now, we don't know that all the 27% where we see these so-called smooth plains. Us planetary geologists are very creative in how we name stuff. So if we see plains that are morphologically smooth, we call them smooth plains. So, and it's complicated, right? Not all the smooth plains are necessarily volcanic, but most of them by area and by volume are. Indirect evidence suggests that perhaps even the older, more rugged, cratered plains on Mercury might actually be older volcanic plains, and the reason they look different is because they're older and they've been churned up by impacts longer. So what we see on Mercury are vast expanses of plains. What we don't see on Mercury are big shield volcanoes. In fact, these volcanoes here, these pictures, perfect to illustrate this, right? This is what we don't see on these worlds. So let's go with the top here, right? This is a volcano. It's an active volcano in Kamchatka in Russia. And if you ask a kid, draw a volcano, please, the likelihood is they'll draw a cone and maybe some smoke coming at the top. And that is sort of the that's not the only kind of shape or style that a volcano can have on Earth, but it is a classic one, right? And a lot of volcanoes look like this. And this volcano in this picture taken from the space station is in fact erupting. This is pretty standard stuff. Get those all over Earth. We tend to see them focused in areas where there are big tectonic structures, and the biggest kinds of tectonic structures on Earth are plate boundaries, and we'll talk a bit more about that in a few minutes when we go on to the next page. But big volcanoes on Earth, check. We know there are big volcanoes on Venus. Now, Venus is the second image here, and just going to give folks a sense of what they're looking at here. We don't have any photographs of the Venus surface from space, and that's because Venus's atmosphere is opaque to visible wavelengths. So the only way we can see the surface of Venus from space is to use radar. In fact, if we were to photograph the surface of Venus, we would have to be within 2 or 3 kilometers of it, because the atmosphere is so thick and probably hazy that we just wouldn't see it, right? So, and even then, that's where we're back to our self-cleaning oven temperatures. So to see the surface, we use radar. And radar data can be processed to look a bit like an image at the end, but it's not quite the same thing. And sometimes things look kind of shifted and skewed, and there are all kinds of things you've got to consider. But in this picture here, what you're kind of seeing is sort of a roughly circular kind of splotch. Again, a technical geological term. And then these sort of kind of like linear things coming off it. And one of the things that controls brightness, or how bright or dark something is in a radar image. This radar image, by the way, they're generally black and white, and you can colorize them. This one's colored kind of yellowy because, well, we assume that Venus is kind of yellowy. They could have made this blue, right? This is just this color that NASA goes with, right? It's not actually this color. But the relative brightness and dark here corresponds to a few things, including how rough something is and perhaps even how old or how young something is. And there are definitely kind of weird, irregular looking things that appear to be radially emanating from this splotch that resemble morphologically, that's that comparative planetology again, that resemble morphologically lava flows on Earth. So, plus we know from topography that there's a high standing thing here. So we call this Sapas Mons, but this is, we don't 100% know that this is a volcano, but it has all the physical characteristics of a big volcano on Venus. So, and that's not really contented, right? I think most of us are happy that there are big shield volcanoes and big composite volcanoes. And I mentioned shield volcanoes there. Shield volcanoes are the biggest kinds of volcanoes on Earth. And the really famous one is Mauna Loa. Yep. But there's lots of other examples around Earth. Shield volcanoes are so called because originally, at least that's what I was told when I was studying this stuff, they resemble warriors' shields. I'm not sure if that's actually true, but that's the story. That's why they call them shield volcanoes.
Oh, that's interesting.
Yeah, right, supposedly. They're super broad. They can be quite tall, but they're far, far broader than they are tall. And you can see that's not quite the shape of, say, Sapas Mons or the Kamchatka volcano. They tend to be more conical. Shield volcanoes might look like this. And if you've ever been to Hawaii, for example, you've been on any shield volcano, even though Mauna Loa is in fact the tallest mountain on Earth if you consider its seafloor height to the summit. Right, it's huge, right? So these things are very broad. Well, the biggest example of all that we know of is this third picture here. This is Olympus Mons, right? Mount Olympus on Mars. This volcano is the size of Arizona, right? You can pretty much fit it right within the boundaries of Arizona. Or when I talk to my European colleagues, this is the size of France.
There you go.
This volcano is about 21 kilometers tall from the plains up to the summit, but it's so big. It's about 650 kilometers across or so. And Mars is so comparatively small, modest radius of curvature, that if you stand on the summit of Olympus Mons, you won't be able to see beyond the base, which means all you'll see is volcano. Right? The base is beyond your horizon. This is the biggest example of a thing that's really common on Earth and on Venus, shield volcanoes, right? These huge volcanoes. And the way we think shield volcanoes are built is that we have relatively runny lava, and the lava pours out of the ground and goes very far. But if you allow this thing to build up over enough time, you do eventually kind of stack them up, but the overall shape you'll get will be super, super broad. The reason we think Olympus Mons is so big is because we think these big volcanoes, big shield volcanoes, including the Hawaiian Islands, are fed by what we call them mantle plumes. And then there's some disagreement as exactly what that is. But we think there's a big conduit of melt from deep inside Earth, or in this case Mars or Venus, that makes its way to the surface and pours out this runny lava. And we know on Earth that this explanation accounts for why there's often what we call chains of ocean volcanic chains or chains of seamounts. And the reason the Hawaiian Islands form a chain is because this plume is relatively stationary, but the Pacific plate on top is moving. And the plume actually comes up in dribs and drabs. And each of those things makes a set of volcanoes. And then the older ones are carried away from the volcano, leaving this chain of mountains.
Mm-hmm.
In the case of Mars, without plate tectonics, we think the plume is stationary relative to the surface. And so this volcano, we suspect, is at least 3 billion years old. And this thing just sat there for an unbelievable long amount of time and just made this huge mountain.
Do we have estimates of the last time magma flowed on Olympus Mons?
I think this is where we have those youngest flows from Mars that are around 2 million years. That was a discovery made with the Mars Express spacecraft. I'm pretty sure it was Olympus Mons. A really interesting study came out a few years ago in which folks looked at what we call paleo flow directions, like paleo meaning old. But basically what they did was, and in fact, this was one of the parts of the focus of my PhD was, as these volcanoes grow, they actually flex or push down the basement. That's just because they're so heavy, they weigh down the crust. And we know that the Hawaiian volcanoes do this, for example. That's a pretty standard phenomenon on Earth, and we know that it happens on Mars too. And interestingly, there are really, really old flows. They're not very well preserved, but you can still see them with the images we have from Mars now. And if you look at the direction those flows go, they don't flow downhill anymore, which is kind of odd, right? Lava really ought to, like any fluid, should flow downhill. But it turns out that if you use a computer model and you basically subtract some of the mass of Olympus Mons going back 3 billion years, you can actually figure out how much deflection there was of the basement when those lavas were originally forming, and they flow downhill if you take a certain amount of mass of that volcano off. Then we look at the well, not we, but the authors of this work, and there's been a few studies like this, look at the number of craters on those flows to approximate their age. And that gives us a sense of what the growth history of the volcano is. It's a really, really neat idea.
Very cool.
And you need high resolution image and topographic data, but they've done it for Olympus Mons. And one of the things it tells us that Olympus Mons is super old. It's at least 3 billion years, which is to say there was a big volcano there already 3 billion years. It's perhaps not quite as big as it is now. So these things are super long-lived. Of course, there are no volcanoes that old on Earth because the oldest ocean floor is around 200 million years, right? It just gets carried away from the spreading centers and subducted and it's gone. And the average surface age of the land of Earth is something like 7 million years or something. And you just tend not to find old stuff because it gets covered and buried in sediment and all that kind of stuff. So again, that's the real value looking at these worlds, is they preserve that record of what's happened over their lifetimes, over billions of years.
Cool.
So this is the page where we can actually talk about where that comparing and contrasting comes from.
Okay.
So we talk about how the goal is to put all 5 together and look at what kinds of landforms they have. And I talk about how Mercury has these expansive plains, but it doesn't have these big volcanoes. Mercury and the moon are similar. We'll talk about that in a moment. But Venus, Mars, and Earth have these big volcanoes. They have shield volcanoes. We have smaller ones that are still quite big called composite cones. And we think that the different kinds of lava with different viscosities that make these more steeper kinds of cones. They have scoria cones, which are these sort of cinder cones, the SP crater in Arizona, for example. There are tens of thousands of these things on Earth, and we suspect huge numbers on Venus and fields of these things on Mars. So certainly, in terms of the kind of characteristic volcanological signatures, Earth, Venus, and Mars have a lot in common. But there are other things too. And one thing that's really worth talking about is where the volcanic properties or landforms and processes have taken place in these worlds. So let's start with Earth here. The kind of Earth is our sort of base idea of a world. Unfortunately, Earth is, in some respects, a dreadful world to start with because it has a bunch of really rather unique things that other places don't have. So in some respects, it's a terrible world to calibrate your thinking on. But let's talk about what we see on Earth. So first off, anything that's kind of colored pinky here is volcanic product, right? I am a lumper, not a splitter. I have been from the very earliest days of my geology training. I was the kind of guy at an outcrop rather than trying to figure out all the different layers. I'm like, it's all one kind of rock, whatever. So I've not made a big effort here in trying to sort of separate stuff out. But all that pink stuff there, that basically is the oceans. That's the ocean floor, because by definition, the ocean floors are volcanic. That's how they get made. Oceanic crust is basaltic. Mm-hmm. You'll notice then there's darker stuff. And some of that darker stuff, that darker red stuff, is on the seafloor, and some of it's on land. And that's what we call large igneous provinces. Large igneous provinces are these really interesting places on Earth. There's a few very well-known examples. The Columbia River basalts, for example, up in northwest US. The Deccan Traps, a lot of your viewers may have heard of the Deccan Traps. They're in India, and they're about the same age as when we know the dinosaurs went extinct. And I think we're kind of beginning to really start to settle the debate now that I really do think it was an asteroid that wiped them out. But they may have been under a lot of climate pressure already. And the Deccan traps in India, they're kind of on the west coast of India, those things are expansive. And what we call trap is an old, I think it might be an Icelandic term, but it's a term we don't use that widely anymore. It means looking like a staircase. And the reason it's called that is because if you ever see pictures of these things, or if you're lucky enough to go and see the outcrop in person, these things are kilometers thick and they look a bit like staircases because they're composed of lavas that pile up on top of each other like this. And often there's a gap of a few months or even years between successive flows, and there might be little layers of soil between them. And then as they get eroded down in today's climate, they tend to form this kind of staircase pattern. So if you Google traps, Deccan traps or Siberian traps, which are really, really big, expansive up in northern Siberia, you can imagine this is 5, 6, 7 kilometers in places of lava that pours out. And one of the things that defines a lip, a large igneous province, is that they come out really, really fast. Within a million years, you could have 100,000 cubic kilometers of rock. Now, a million years is not fast in normal people's terms, but geologically, a million years is not very long. And to produce 100,000 kilometers cubed of basalt or more in a million years, you're talking about huge effusion rates. And one of the reasons these things are really important to study is because when you erupt basalt really anywhere, which is your standard volcanic rock, basically, basalt is a basalt, you produce a whole pile of gas too. And those gases they do all kinds of things. You can water, vapor. And in fact, this is probably one of the ways in which we generated the atmosphere we have today. But you also generate SO2, which is known as an icehouse gas, and SO2 can reduce global temperatures. In fact, there have been eruptions in the 1800s in which the following year or two in Europe, they call it the year without a summer because you have this huge injection of SO2. And for about a year or so, your global temperatures drop by a few Celsius. Now, SO2 is a short-lived gas. Within a few years, it dissipates. You also produce a lot of CO2. And of course, we all know that CO2 is a greenhouse gas. And so, although a volcanic eruption may cool the atmosphere of a planet for a time, it longer term is actually contributing to heating up the planet. If we've got time, we might kind of come back to that point for Venus at the end. The point is, LIPs are big deals. And some of the biggest mass extinctions in the fossil record preserved in Earth history are temporally associated and are probably caused by these masses of eruptions. Right? So LIPs are big, you got to include them as well. But if you go back to the picture of Earth, you also notice there's a bunch of yellow dots around the place, and we call those things hotspots. And hotspots are usually not at plate boundaries, which I'm going to come to in a moment. And they're basically places where volcanism just comes up in the middle of a plate. And the Hawaiian Islands are a great example that most people are aware of. There's no tectonic boundary anywhere near the Hawaiian Islands, but there's a huge volcanic complex there. Because sometimes this stuff comes out of the lower mantle, deep inside Earth, about halfway down, and just goes, I'm coming up here. And it does.
Out of the way.
Right, that's what exactly, yeah. And you have to, because it's going to go out there anyway, so you don't want to be in the way. But you'll notice there's another little dot there called volcano, and it's a little black circle. And if you I realize these pictures are small, and if you kind of get access to this thing, you can pull up your face. But there are black dots all over the place, and they are volcanoes. Right, exactly. And here, and this is something that a lot of kids see in their school textbooks. A lot of these black dots, and a lot of them are associated with big plate boundaries. Right? There's a whole chain of them going right from Alaska all the way down the side of South America, down to the bottom. You see them in Indonesia, and the Philippines, Japan, New Zealand, all the way up into Russia. You see them down through East Central Africa, where the big East African rift system is.
Yep.
The point is, these things are not always, but often, controlled by big tectonic structures. And the biggest tectonic structures on Earth, like I said, are plate boundaries. Right? Divergent plate boundaries are shown in this kind of green color. And then you'll notice there's some other thinner black lines. It's other plate boundaries. There's 3 main types. But importantly, the green stuff, which is divergent, meaning where the plates are coming apart, that's where you're making new crust. And that's where you have, there are discrete volcanoes, but there are hundreds of thousands of places where stuff is coming up that aren't shown here, that are shown here. So let's kind of wrap up what we see here. We see a whole pile of volcanism, a whole pile of stuff coming out of the ground. We see lots of places where volcanism is manifested in individual sites. These hotspots are volcanoes. The hotspots seem to kind of be everywhere, but we'll see that the volcanoes are often controlled by these big tectonic structures, and we get these lips, right? These structures that are both on land and also in the sea. So that's kind of Earth so far. Okay, so if we scroll down to Venus, let's see how Venus and Earth compare. All right, so first off, we're seeing there's a whole pile of this pink stuff, right? This stuff is all over the place. Venus' surface is kind of weird. And the reason it's kind of weird is that it doesn't really look like the surfaces of other planets. One of the things you might think of when you think of Mercury or the Moon, or really most places like that, is you're thinking impact craters. Venus has about 1,000 impact craters, 960 or something like that. And that's really not very many. That's surprisingly few. One of the surprises, actually, one of the big surprises out of NASA's Magellan mission, which was the mission to image with radar almost the entire surface. Magellan got to Venus. It was launched in '89, and it got there in 1990, or began operating in 1990, and operated through, I think, 1994. And it returned 98% of the surface with radar. And one of the really surprising things was how few craters there were. The reason we think this is most of the surface of Venus, in one form or another, is volcanic material. And that's why almost all the surface here is colored pink. So you can see this stuff is everywhere. And the color system is sort of similar here, the kind of purpley stuff. That's an extensional structure or system. There are these things, so I mentioned that there's a thing called the East African Rift Zone. Rift zones are really common on Earth, and you know, we have rifts in the Basin range in the western US, for example. Rifting is basically exactly what it sounds like, where chunks of the crust come apart. There's a huge system of rifts that kind of spans about 2/3 of the equator, or low latitudes around Venus, and it's this purpley stuff there. And it's extremely complex in terms of its tectonics and its morphology, but if you just lump everything together, you can kind of color in the purple as rift zone stuff, right? That's where the crust is pulling apart. You'll also notice that there are black dots, which are volcanoes, everywhere. Now, there are some places that are white. That's older stuff that I'm not really going to talk about right now. It's not volcanic, or if it is, it's older versions and we don't consider it as volcanic. And you'll notice there's two kind of strips of white at the top. That's where we don't actually have radar coverage, right? Just this is how it looks in this projection. But the point is, pretty much everywhere there are these volcanoes everywhere. And this is an incomplete, this is a data set of fairly large volcanoes that's been published. This is not all the volcanoes. And the way the image for Earth is not all the volcanoes. This is represented of the fact that there are volcanoes everywhere. There is lava everywhere. And there are these huge rift zones where the crust is being pulled apart. There's also this yellow category, these yellow squares called corona. Thankfully, nothing to do with the virus. These things are, corona are weird. Honestly, actually, a lot of stuff in planetary stuff is weird. And I'm going to say several more things are weird. They're these kind of weird circular things that are, you can see there's yellow everywhere. In fact, the yellow and the black dots often line up, but these yellow things are these weird circular-looking structures. In fact, a paper came out only a few weeks ago suggesting that some of these things, we think they're volcanic, because in lots of places we see lava, young lava, lava that looks relatively fresh on the basis of its radar data, and therefore could be young, that's spatially associated with these things. And a paper came out in Nature Geoscience a few weeks ago suggesting that at least some of these corona, the ones that the authors looked at, might even be active today. There may be an actual source of magma situated underneath that thing that's producing this weird kind of, almost like a blister, right? Some of them have a kind of raised dome, some of them are a ring. There's a different variety in how they form, but, and we don't really see an equivalent of corona elsewhere in the solar system. Right. But they are, we think, volcanic or somehow tied to volcanism. So we count them for that reason. The point is, they're everywhere, right? You don't really see places on Venus where there's a dearth of volcanic stuff. There's a few places, we call those the tesserae, but we're going to leave them aside from now, right? But in the main, lots of stuff all over the place, and the crust is being pulled apart, right? That's the purple stuff. So that's Venus. All right, so let's scroll down to Mars now, and let's see what we see in Mars. Okay, so there's much less pink here, but these are all the units we know are volcanic. I think if you talk with people who study the history of volcanism of planetary surfaces and how planets get their crusts, the way, at least in my view, the leading way that you get a crust at all is you have volcanism. So the units that are white here, or that are not shown, this is taken in part from the global geological map of Mars that was published 6 years ago. It's not to say that they aren't volcanic, it's just that they're not the stuff that's pink here is some of the geologically younger volcanic material. Younger can still be, depending locally, be quite old. But we know this stuff is volcanic. First off, there's a lot of it. Right, certainly you're seeing about a quarter, a fifth of the planet in these sort of volcanic units. You'll notice the single biggest splotch of it is on the left. That's the mighty Tharsis region. And Tharsis is home to Olympus Mons and 3 other really stunningly huge volcanoes. But there's a sort of smaller, but still significant splotch on the right. That's Elysium. There's 3 very large volcanoes there, and there's sort of smaller other splotches. Particularly there's 2 near Hellas, called the Circum Hellas volcanic province. Other things I want to point out, there's individual volcanoes shown in these black dots. The black dots are not scaled to volcano size, so you can't really see the really big volcanoes here, but they are here. But you'll notice there's a cluster of them in the north, and there's clusters of them over in Tharsis, and there's a few down here in the south, and there's a bunch of them all over the place, right? We don't see them particularly restricted to one place or one region of the planet. And also you'll notice there's some pretty big circles here. And those circles are all the craters on Mars, 200 kilometers in diameter, which is giant, right? It's like 120 miles across. 200 kilometers in diameter or bigger. And you can see there are some really big ones. It's possible that, in fact, the entire northern third of Mars is a single impact crater. I don't show it here because it doesn't really influence the story. And it's also not, we don't know that for sure, but it's possible there's a really big crater there. But you'll see there's a pretty big one in the south. Hellas is the largest definitive or confirmed basin, but there's some other really whopping ones.
Yeah.
But I want you to notice that in some of them, there's some volcanism nearby, and in others there isn't. And in some, there's volcanoes nearby, and in others there isn't. And also notice the purple stuff. Just like for Venus, this purple stuff is extension, right? It's where the crust is being broken apart. It's not nearly as extensive as you see on Venus. You don't have these huge planet-spanning rift zones, but you see lots of places on the crust all over the planet, particularly in Tharsis, where the ground has been pushed apart. So that's an important thing I want you to notice as well.
Cool.
All right, so that's Earth, Venus, and Mars. Now let's go to Mercury, and let's see what Mercury looks like. Okay, so this is Mercury. Now, Mercury is a lot smaller. These are all shown at the same scale in terms of like the printing, but Mercury is Mercury is bigger than the Moon, but it's a good bit smaller than Mars, right? So Mercury is quite a small world. So a few things to notice here. First off, all the pinky stuff, that's volcanic material, right? And these are the smooth plains that I was referring to. Now you'll notice there's also some gray splotches all over the place. They are also smooth plains, but they're ones that we don't yet know, at least when this paper was published, we don't yet know for sure that they're volcanic. I suspect most of them are, but we don't know, so I didn't include them, right? You'll notice there's still a lot of white. That white, I think, that's largely made of this a terrain type we call intercrater plains. It's not a particularly descriptive term. It's older, much more ruggedized craters terrain. I think most of it's volcanic too, but we don't know that for sure, so we don't include it, right? So there's all our known volcanic stuff. You'll also notice that there are some sites of explosive volcanism. So you'll notice there are yellow circles with red outlines, and they're distributed around the place. One of the really surprising things, and I kind of glossed over this before, you know that we have big volcanoes on Earth that produce this nice effusive lava. And if you look at the back to the cover picture of the article, we have nice, we call it basaltic lava. It glows in the dark, and you see it in Hawaii. It's really cool looking, right? But we also know from movies like Dante's Peak and other dreadful disaster movies that volcanoes can also explode. And the key determiner of whether or not a volcano will explode is what its volatile content is. Volatile is a catch-all word we use to describe basically the stuff that's gaseous inside lava, and it's water, it's SO2, it's CO2, it's the gases that come out of this stuff. Depending on how much, what your volatile content is, and also what the composition of the lava is, although that's less important than its volatile content. The magma can explode violently, and that produces these explosive eruptions. Water inside, when water gets into a magma chamber, that can really drive up the volatile content of magma, and that can make volcanoes extremely dangerous. For example, a lot of the ones around the Ring of Fire, right, particularly in Indonesia or in Japan or in New Zealand, those volcanoes often erupt explosively. They can also erupt what we call effusively, where nice, slow, runny Hawaiian-like lava comes out, but they can erupt violently. And that's because those volcanoes are situated at subduction zones where water-rich crust gets subducted, and if some of that water makes its way into the plumbing system, it will drive the volatile content up, and you can get explosive volcanoes. Mount St. Helens is a perfect example of a volcano that blew its top, or its side, really. But these things can be catastrophic and pose a real geohazard to humans.
Or Krakatoa.
Krakatoa, right? The boom heard around the world. Absolutely, right? So these things can be devastating, and they can cause huge untold destruction. And we saw Anna Krakatoa went off at the end of 2018. So, you know, this is a fairly routine thing we see on Earth. We don't know much about explosive volcanism on Venus. I mentioned earlier that Venus's surface temperature is like self-cleaning oven, but Venus's surface pressure is the equivalent of about 1 kilometer under the ocean on Earth. So the high pressure, it is thought, may actually inhibit those volatiles exploding out. So it may be that if you have volatile rich magma on Venus, perhaps it actually doesn't explode. That's an open question. I don't know if we can definitively say we know that for certain. Mars has definitely had explosive volcanism, and I suspect there are people working right now who suggest that there may be some parts of Mars that are way more expansively covered in explosive volcanic material than we recognize to date. So that's kind of an open question too. This is an exciting part of planetary volcanism, is just how prevalent are explosive eruptions. We do know that they have happened on Mercury. And the way they're manifest on Mercury is they're never gonna make these big cones. But what they do instead is there's a bunch of really weird places on Mercury where we see these irregular holes. Now there's lots of holes in Mercury, right? There are craters everywhere. Craters are generally fairly circular. But it turns out that there are lots of places on Mercury where the holes are very irregular and they do not have a raised rim, which is something you get with an impact crater. With a meteor crater, you'll see the rim is raised because that's how stuff gets thrown up. These things don't have those raised rims. And they often have, we took photographs of the surface of Mercury in color, different color wavelengths. And we often see places where there's a brighter color of what looks to be a fine material circling these holes. And that's exactly what you'd expect to get if you had a fine, volatile rich material that comes out and settles back down, basically volcanic ash. And so, until we go there and land, it's never going to be a closed question, but we think these are sites of explosive volcanism on Mercury. There's a few things I want to point out in terms of where these things are located. So you'll notice that these big splotches of this pink stuff, right? There are virtually no sites of explosive volcanism inside the pink, right? So that's one thing to notice. There's a few, but very, very few of them. Most of them are either along the edges of big impact craters, right? So you'll see there's a big thing here on the right-hand side called Caloris. Caloris is the single biggest recognized impact basin, right? That's it there. Caloris is big enough that you can fit Western Europe inside, right? It's 1,000 miles across. It's absolutely huge. You'll notice there's a bunch of yellow dots around the edge. That is exactly where we might expect to find explosive volcanism because of what I'm going to talk about in a few minutes about a prevailing stress state. So that's something that's not that surprising. And one thing that's not shown on this map of Mercury is that there are huge tectonic structures. And this is where the tectonic starts to kind of work its way in. There are huge tectonic structures, huge cliffs or scarps, we call them, all across the surface of Mercury. And these things form, we think, because Mercury has shrunk. And I'll get back to why Mercury is shrunk and why this matters to volcanism in a moment. But what's really interesting, exactly like imagine like a prune. Like a prune shrinks and gets wrinkled because it runs out of water and gets smaller that way. So it's not quite the same phenomenon. But as a prune decreases in volume, its surface crinkles up. And that exact phenomenon is what's driving or has driven the formation of these massive scarps all over Mercury. Now, they're not shown in this map because it gets too cluttered. But where those yellow dots are that don't really seem to be anywhere near anything else, they are all along these big structures, right? And there's a few other things that are worth noticing. We've seen on these other basins, on these other worlds, particularly for Venus and Mars, but also Earth, that there's lots of places where the crust is being pulled apart, right? That's that purple color. Same here. There are extensional structures on Mercury, but look where they are. They're almost entirely within Caloris, and there's a few smaller splotches in a crater that's kind of halfway down on the right-hand side, and there's a few splotches of them in Borealis Planitia up in the very top of the picture, right? Yep. Borealis Planitia is the single largest deposit of this smooth plains material. In fact, Borealis Planitia is about 6% the surface area of the planet. And when we look at it with craters, we don't see any geological units anywhere inside it. We actually don't see any places where we could draw lines. And what that tells us is within the resolution we have of craters, that Borealis Planitia was made in one go geologically. Now that might have been a million years, might have been 5 million years, but in one instant, geologically near instantaneous event, 6% of the planet's surface got resurfaced by lava, right? So that's the kind of scale we're talking about for some of the magmatism on Mercury, right? So we're seeing a few things. We don't see extensional structures anywhere outside impact basins. We see a lot of this lava, this pink stuff, inside or near impact basins, right? All the Caloris is filled in. There's a huge ring of smooth plains around Caloris, which we think are tied to the formation of the basin. And then you'll notice even in the southern hemisphere, in the left and right-hand side, there are circles where there are these pink deposits, right? With the exception of Borealis Planitia, we don't really see big splotches far away from big impact craters. And I, for one, think that Borealis Planitia itself is actually an ancient impact basin. The northern hemisphere of Mercury, the north and south poles are about the same elevation, right? Because all these worlds tend to be a little flattened at their poles. Right. But the depth or the thickness of the lava that makes up Borealis Planitia, which just means northern, I think it's northern plains, Borealis, Aurora Borealis, or Australis. But these plains are about 1 kilometer or 2 kilometers thick.
Okay.
If you peel those plains off, you have a hole about 2 kilometers. And you don't have a corresponding set of plains in the southern hemisphere. So if I'm right and it is an impact basin, it's ancient. I mean, it's the oldest thing left in the world, on that world. But if I'm right, it's another example of where large volumes of lava happen to be associated with impact craters, right? So we don't see much cracking apart of the crust anywhere outside of these impact basins. We don't see any volcanoes, these cones or these shields, we don't see those at all. And where we see explosive volcanism, it happens to be where we know there are lots of tectonic structures. Either these big scarps that form when one bit of the crust pops up over another, or around the edges of impact craters. And we know impact craters are sites of extreme fracturing because of the terrific energies involved in making a crater in the first place. Right? So that's already quite different. One more thing. All the pink stuff here, all of it's younger than about 3.94 billion years. Okay. And none of these pink units here is younger than about 3.5 billion years. Right? So all the pink here got in place from around 4, 4.1, 3.9, it's not quite clear when. But all of that big stuff was in place by 3.5 billion years ago. Now, if those other pink or gray splotches, some of those, in fact, there's at least one we know definitively is probably as young as a billion years, but it's volumetrically tiny, right? Most of the volcanic action on Mercury happened and was over by about 3.5 billion years. Now, an interesting observation is these scarps, right, that are all over the planet's surface of Mercury, these things we think form because the planet contracts, right? We call it global contraction, it's the term we use. Right. This is happening simply because, like any object that's hot, as it cools down and it radiates its heat to space ultimately, it just simply gets smaller. And we know that Mercury's gotten smaller because we've done analyses where we can look at the heights and the lengths, the sizes of these scarps, and we can add them up and we can make some assumptions. We can work out actually how much of the radius has changed. We think Mercury's radius is decreased by several kilometers. Now that may not seem much. Its radius is 2,440 kilometers. But if you're losing even, 0.5%, 0.25%, that's a lot of planet to lose just by virtue of its cooling down and shrinking. And we don't know for sure when this started, and that's one of the big open questions we have for Mercury. But on the basis of seeing lava cut across these scarps and see these scarps cut across lava, we're pretty sure these scarps formed, or at least had started to form, around the time lava came to an end, the emplacement of lava came to an end on Mercury. Okay. And one of the predictions that people made a very long time ago for planets, and in the case of Mercury back in the 70s, was that around the time a planet starts to cool down and it starts to shrink, it's going to get really, really hard for lava to get to the surface. Right, now I'm going to leave that topic for now there. Let's go on to the moon, and then in a few minutes we'll revisit what happens to lava on a planet that's shrinking. All right, so here's the moon, Earth's moon. So first off, there's a lot of pink again here, but bear in mind, of course, this is ever decreasing actual amounts of pink because these worlds are getting progressively smaller, right? The moon is the smallest of these 5 worlds. So this is the prime meridian right in the middle, right, 0 degrees longitude. This is the bit that faces us, right? As you know, the moon is tidally locked to Earth. So we on Earth only ever see one side because its period of rotation matches its period, its orbital period. And on the lunar near side, all this pink stuff is what we call the lunar mare, which is Latin for seas. But if we didn't know that term and it didn't go back to antiquity, we would call these smooth plains, right? This is the same stuff we see on Mars, on Venus, dark stuff, dark basaltic stuff, right? In fact, if we didn't know better, we'd call them smooth plains on the ocean floor.
Yeah, exactly. We call them seas.
It's the same stuff. It's just magma that comes out of the ground, and standard composition magma is basaltic, right? There's lots of exceptions, but in the main, it's basalt. So what else do we see here? Okay, well, all the craters bigger than 200 kilometers in diameter are shown by these circles. You notice this really weird kind of like almost sinusoidal looking thing around the bottom. That is South Pole Aiken Basin. That is, I think, the largest recognized impact basin in the solar system, and it is absolutely huge. And it's called South Pole Aiken Basin because it goes from the South Pole up to Aiken Basin. So you can see that it really is an absolutely gigantic structure. You'll notice, though, there's a lot of basins on the near side, right? There's Tranquillitatis and Serenitatis basins where the Apollo astronauts went to. You'll notice that in many cases, the lava, which is this basaltic stuff, is either partly or completely contained within these big circles. There's a notable exception to this called Oceanus Procellarum, which is, or sometimes people call it Oceanus Procellarum, which is labeled here. This is this kind of weird north-south kind of trending thing. So you'll notice there's these big circles are full of mare, full of these basalts. Oceanus Procellarum, some people have proposed, even to this day, some people think there may still be a really, really old basin that isn't quite preserved anymore that you can't see. We do know this is an area where the abundance of heat-producing elements, the stuff that when it decays, melts, generates heat, and therefore generates magma, is concentrated in Oceanus Procellarum. I'm not sure we exactly know why that is yet, but we do know that's the site of some of the most recent volcanism on the moon, most recent being, you know, within the last 2 billion years or so. But you'll notice that there really are whole parts of the body of the moon where there are no basaltic volcanic products anywhere. You'll notice that there is very, very limited, there are virtually no volcanoes in the conventional sense. There are these things, there's a few ones that were identified in the last 10 years that may be shield volcanoes. Remember, the shield volcanoes are characterized by being not very tall relative to their breadth. These things, there's a few of them. You can see there's a few dark ones. There's a few examples over the word Oceanus there. They're so subtle, you have to have high resolution topography to see them. You cannot just look at them. It's certainly not like Mars and Moon, Mars, Venus, or Earth. Right, these things super subtle, right? And we can't rule out that there aren't something similar on Mercury. We just don't have the resolution to tell. But we know there are these little kind of cones. Not really. There's a few of those things on the moon, but not very many, and certainly not the size you get on the other 3 larger worlds. There are sites of near-surface volcanism, sites of explosive volcanism. That's the yellow circle again with the red outline. The vast majority of those are either inside or around the edges of impact craters, where we know there's lots of tectonic structures and along which magma's ascent can be facilitated. There are sites of near-surface intrusion. That's the blue squares. These things form what we call four-factor craters. Now, all the craters shown here are, I think it was 200 kilometers and above. That's the threshold. There are obviously millions of craters below that threshold size on the moon and on these other worlds. So where you see the blue squares, what you're not seeing is a small crater that those squares correspond to. But in lots of examples of these craters, either inside the entire floor or around their edges, there are places where you've got evidence for an intrusion, right, which is what we call magma before it reaches the surface, right? It's magma inside, it's lava on the outside, but sometimes what happens is, as it fills in, it bows the ground up, but it doesn't actually erupt. Or maybe a little bit of explosive eruptions happen, but you don't get a big lava flow. But you get this kind of dome. So there's lots of places where those things happen, but they happen inside or in association with pre-existing impact craters, right? Places, again, where there's lots of fractures where the crust is weak. And we don't really see extensional structures, right? There's a few places where you see purple lines. Most of those purple lines happen to be where that lava flow and the lava infill in those basins pushes the ground down. And if you imagine taking a trampoline, right, and you stand in the middle of a trampoline, you stretch the edges down, right? That's when springs go all the way down. That stretching locally is a perfect place for volcanism to come up. You see the same thing. Remember, we looked at Mercury, where we have these explosive things around the edge of Caloris. You see something similar here. There's a few places where there are extensional structures outside of craters, but the vast majority are inside or radial or concentric to these basins. What you definitely do not see are huge rift zones that span across the lunar surface.
Right.
Like you see on Mars, like you see on Venus, like you see on Earth. You don't see that on Mercury, you don't see it. And tellingly, most of that pink stuff, not all of it, but most of it by volume, was in place by around 3 billion years, right?
Okay.
There was a pulse around 2.2 billion years, and there's been some stuff. There may even be volcanism as recent as 100 million years on the moon, but again, volumetrically tiny, right? Most of the action was over around 3 billion years. So when we look at all 4 worlds again, we see the 3 on the left-hand side. We have Earth, Venus, and Mars. We have volcanism all over the place. We don't see volcanism concentrated inside impact craters. We see shield volcanoes, composite volcanoes, scoria cones. We see lots of extensional structures. And we see a history of volcanism. One thing I didn't say is some of the stuff on Mars is a few 100 million years old. And some of the stuff on Venus, and this is kind of the open question, some of the stuff on Venus, the average surface age of Venus is 700 million years. That's pretty old, right? But that means there are some parts of Venus that are probably a few billion years old, and some parts of Venus that may be a few tens of millions of years old. And circumstantial evidence suggests that volcanism might be taking place on Venus today. There's a few different lines of evidence. One of them is, if you look at my background here, which is the picture of Earth that I colored, but it's supposed to convey the idea of what maybe the Venus atmosphere might look like. Venus has this global cloud layer. right? I mentioned earlier that you can't see through this with visible spectrum images. You have to use radar. This global cloud layer is largely composed of sulfuric acid clouds. Sulfuric acid, we think, is coming from a combination of SO2 and H2S and H2O, stuff that comes out and is known to come out of volcanoes. None of those compounds is stable in the atmosphere for hundreds of millions or billions of years. The sun breaks it down. But this global cloud layer seems to sort of be there, right? Which kind of implies that the stuff, the chemistry that goes into making it is being replenished, right? And the way we know to do that is volcanism. Venus Express, which is an ESA mission that operated from, I think, 07 or 06 through 2015, 2014, somewhere in there. At Venus, Venus Express carried on board instruments that were able to, the mission was a largely atmosphere-focused mission. Like I said, the last mission dedicated, focused on the surface of Venus was Magellan, launched 30 years ago. But Venus Express was able to look at the spectral properties. It turns out there are some wavelength windows in the infrared that you can see through the Venus atmosphere. You get a lot of scattering, so you don't get high resolution, but you can see the ground in infrared under a certain wavelength, through certain windows through the atmosphere. And evidence from Venus Express suggested two interesting things. One, that some of the lava flows have what we call an emissivity when we looked at infrared that might correspond to them being relatively young. Now, we've no independent constraint on what relatively young means, but not millions or hundreds of millions of years, perhaps 100,000 years old, perhaps even younger.
Okay.
And also indirect evidence for what were termed transient thermal anomalies. It looked like we were seeing some parts of the surface get warm and then get cold again. Relatively speaking, the whole surface is self-cleaning over, right? So we're seeing little temperature spikes that don't last very long. That is consistent with what you might get if you had volcanism going. And where we saw that high emissivity lava that might be relatively young, where we saw those thermal anomalies, happen to be situated spatially near where that purple stuff is in Venus. These huge rift zones, which would be the prime place to look for lava, as we know on Earth. You want to look at some of the youngest lava on Earth, you look at the spreading ridges, or you look at the East African ridge or other continental rift zones on Earth where you get young volcans. So we don't know for sure, but there's a lot of indirect evidence that there may be volcanism taking place in Venus today. And I, for one, I've turned into a bit of a Venus evangelical over the last few years, but I think, sure, Venus is, in fact, I'd be astonished if Venus wasn't active today. So that's Earth, definitely active today. Venus, probably, but certainly relatively recent. Mars, some flows there, perhaps as recent as 2 million years, but certainly within the last few hundreds of millions of years, lots and lots of lava. Mercury, almost all the action over 3.5 billion years ago. Most of the volcanism situated within pre-existing impact craters. Very, very little evidence for extension of the crust, and almost no volcanoes in the conventional sense. And a very similar story for the moon. And exactly what you've got down here in this little box, this is sort of a timeline. Now this is best guess, and it's semi-quantitative, right? It's really, really hard to say exactly when, you know.
Sure.
Please don't get in touch and don't reach out in 50 years and say, hey, that bar should have been 3 millimeters to the left. Yeah. But the point is, red, major plains of volcanism, and I'm using plains of volcanism in the broadest sense. I mean, lots of stuff pouring out of the ground, right? That goes from around at least 3.6, 3.7, 3.8 to today. The yellow bar that brings you back up to 4.5 when Earth essentially got formed, suspected volcanism. I mean, Earth has probably been volcanic the whole time. Of course, we just unfortunately don't have evidence of that. Venus, suspected volcanism through today, at least this author suspects it. You've got this little bar of red, major plains volcanism, because that's the model age, that exact nubbin there. 750. We have so few constraints because there are so few craters. We don't really know the actual age of things, right? So in real life, there's no way that bar. I don't want to get into this rabbit hole, but there for a while, and I think even to this day still, is a school of thought that in fact Venus was resurfaced in one go. I really don't think that happened. So I don't mean to suggest with this tiny little red bar that it was just like, you know, one day Venus went, oh.
Yeah, spike.
Right. It probably is more, you know, one part and then another part. And I think if I had my way, and I'm hoping, you know, with missions in the next 20 years perhaps, we'll know that we could actually change the yellow to red. Right? And then because we don't really see much of ancient Venus preserved, I say unknown but suspected volcanism. That's kind of pale yellow bar. But I would bet good money that just like Earth, you go right back to the beginning of Venus, you have volcanism. Right? Two big volcanic worlds. Mars, well, suspected volcanism, but it's not really clear what happened from 4 billion to beyond, because again, it's hard to know. There's not much of Mars left that old. But you have this major plains volcanism bar that stretches from around 4 to around 1.5. Right? That's the age of those big splotches there. And then intermittent volcanism is that pale kind of salmon colored, pinky color, right? That indicates that, sure, it's not widespread, huge portions, percent of the planet resurfacing and go, but you have smaller volcanoes going off, right? So this is a volcanic world and probably is to today. Mercury and the moon, on the other hand, those red bars are much shorter, particularly Mercury, right? Again, for Mercury and the moon, we don't really know what happened from 4.0 to 4.5 billion years, right? Again, it's very, very hard to understand the earliest phases of these planets' lives. The red bar for the moon runs around 2.5, but like I said, in terms of area, that really should end around 3.5. But we do know that there was a pulse around 2.5. Mercury, though, it looks like most of the action's over by 3.5. And that pink bar runs to 0, because that's not to say that there's nothing happening, but you're certainly not getting these huge, major deposits in these worlds. And I think on the next page, the kind of second part of that box sort of summarizes basically what we're getting at, right? So here you can kind of see total planetary volume, crust and mantle volume, and planetary shrinkage. The goal here is not necessarily to kind of say the exact size of these worlds governs how much volcanism you get. It probably seems like a really obvious thing to say, that the bigger the world, the more heat energy you may have, and therefore the longer you live. Right. But at the same time, it's not nearly that straightforward. And you can't take these worlds' total volume, or crust and mantle volume is given there too, to the nearest 10 billion cubic kilometer. Crust and mantle is where we expect the radiogenic, the heat-producing elements to reside, right? So that's where most of the later, there's always some heat from the core and from the energy of accretion in the first place coming out of these worlds. But certainly we know from Earth, most of what we're getting is generated by heat, radiogenic decay from the mantle and the crust. But it's not a straightforward thing. If you take the planet's sizes, whichever property they have, how much they've shrunk, or how big their mantle or the crust is, or even how big they are overall, and you plot that against the duration of volcanism, you don't get a straight line. You don't get some equation that says, this is the rule governing all planets, because planets are never going to be that straightforward.
Sure.
But what we can say at the end of all of this, when we compare and contrast these worlds, is that as planets cool down, they don't just start to have a case where volcanism starts to kind of drop off in the amount of it, but you still get it everywhere. You start to get very specific types of behavior. You start to localize volcanism in places where the crust is weak. You start to cut off the amount you get. And in some places, you stop making the crust open up entirely. And that's the other aspect of all this in here. And this is why the article is called the fate of volcanic worlds. You could also call it the fate of tectonic worlds. Tectonism and volcanism, right? Tectonism, where rocks break, and volcanism, where rocks melt. They're two sides of the same coin. And if you ask someone who studies volcanology on Earth, they'll tell you most volcanoes are near tectonic plates. And if you study most people who study tectonism, they'll tell you a lot of tectonic activity on Earth happens to be associated with volcanic activity, because sometimes one controls the other. And as you get a world that runs out of energy and starts to cool down, it doesn't just start making less volcanism. It starts to shrink because it cools down. And that shrinkage starts to squeeze off the conduits you would use, right? Now, this is where I said we come back to this point, right? When you have a planet that is humming along like Earth, and the stress state in the crust is fairly neutral, right? In places, the crust has been pulled apart. And when you're pulling apart, you're actually helping lava get up. And in places, you're pushing it together, and it's really hard to get lava. Might kind of make sense, right? And in other places, it's kind of neutral. But the net stress state of Earth's crust is about neutral, right? We have no problem getting lava up to the surface. As you start to contract and cool, you will push the entire surface into compression. Right. Every bit is pushing against every other bit. That's what's making these big scarps that pop up, right? These wrinkles in our prune. And as you're pushing it together, whatever conduits you used to have that lava could easily use, they start to go away. It doesn't mean that you get no lava, but you suddenly start to seriously reduce the amount of lava. Now, you're reducing the amount of magma you're making anyway, because you're getting cooler, you're running out of energy. But you may find that like the inner part, the mantle might start to contract. The crust might not. The crust might still be producing melt and getting stuff onto the surface, but the planet overall is contracting. And what that means is the last gasps of lava coming up are more likely going to come up where the cracks are, where the crust is weak. And that's going to be things like huge tectonic structures, where you've got this big crack going into great depth, or around and inside impact craters, where these fractures, which just formed, they may have formed a billion years before, but suddenly you have fractures that allow you to get up along those cracks. So the idea basically is Mercury bears out this story, and the moon does too. The moon not quite as much. The moon probably hasn't shrunk nearly as much. Mercury looks like it's shrunk much, much more than the moon has. But they've both had this phenomenon of global contraction. And what we see is most of the lava shuts off. Most of the later stuff is inside impact craters and basins. There's very little evidence for volcanoes in the sort of conventional sense, and certainly no big shields that take billions of years to form. And we don't see much evidence of the crust being pulled apart. Most evidence of tectonics, if we see any, is where the crust is pushed together. And that is absolutely not the same pattern we see on Earth, on Venus, or on Mars. Even though Mars is probably shut down in the main, more so than Venus and Earth has, most of the volcanism, the younger stuff, is not inside impact craters. There's plenty of big shield volcanoes. There's plenty of places where the crust has been pulled apart. And a lot of that volcanism has taken place in the last billion years. So the goal of the whole thing of trying to figure out the fate of volcanic worlds is, what happens when a planet gets old? This is a nice example here, by the way, of Mercury. You'll see here there's a crater. You'll see here that the inside of that crater, which is sort of like, you're looking here at an angle, right? But that line right where your cursor is, that's one of those scarps. And in this picture, the sunlight's coming from the left of the image, right? So the right-hand third of the image is black because that's sky, or that's nighttime. We're looking at the terminator, right? The day-night line. And because the light's coming from the left in this image, you can see where the craters are, that their west-facing walls are illuminated in sunlight. And the fact that this scarp is dark means because the light's coming from the left, this must be, the left-hand side must be sitting up on top of the right-hand side. Mm-hmm. It's the only way that kind of shadow makes sense. That's one of these scarps, and it cuts right through this basin. And importantly, the scarp is younger than the lava flow, the lava that filled that crater. Right? And I'll say why. There's two reasons why. One is the crater must be filled with lava, right? Because you can make impact melt. When you make a crater, a little bit melts, but the amount of melt you get is not very much. This crater looks like it's filled almost up to the rim. And I really should call this a basin. This is much bigger than a crater. Planetary geologists each will have their own preference for whether you call something a crater or a basin. I typically kind of say if it's bigger than 100 kilometers, it's a basin. This crater seems too small to describe Calorus, right, which you could fit Europe into.
Right.
But this thing should have either a central peak, a central mountain in the middle, or even a ring of mountains. In fact, this is probably big enough to be a central peak or a peak ring basin, which is a weird series of mountains you get when impact basins form. And I don't see any evidence here. And that suggests this thing is filled right up. And there's no way impact melt will do that. Just you'll never fill a basin like this. The only way you get a basin that looks like this circle, is you fill it with lava after you form it. After it's cooled down, it's a hole, and you pour in lava. In fact, my guess is you poured in lava in the entire landscape here, and it just happened to make its way into the basin and fill it up. So I know the lava is younger than the basin, but I know the scarp is younger than the lava, because otherwise the lava would have come in and filled everything off, right? But here, the scarp is definitely deformed and popped up one part of that lava infill over another. So I know the scarp had to come later. And because we know these scarps on Mercury happen because the planet's contracting, we can say that that lava was in place before the planet contracted. And that is essentially the relationship we see everywhere across Mercury, which is completely consistent with the idea a world that for the first billion years of its life vomited out prodigious amounts of lava. But as contraction started to take hold and the planet began to shrink, you're still producing some amount of lava, but you get less and less of it. And you get ever more of it concentrated inside impact basins until eventually the process comes to an end. The planet continues to contract. A big question we have is whether Mercury is still contracting today. It might well be. But one thing is for sure is any lava that's come out of Mercury in the last 3 billion years was very, very small. And almost all of it was situated in places where we know the crust is weak. So that's one of the things that really separates Mercury from the other 3 larger planets, and that Mercury has in common a lot with them. So the reason this is, who cares? Okay, well, 2 things. One, it helps us understand what we see and why we see what we see. It helps us reconcile the tectonic and the volcanic observations we make of these worlds, right? We can put all of these things within one framework. It helps us understand the timing, why the lava came out where it did, when it did, why the tectonics look the way they do, why we don't see huge rift zones on Mercury or the moon, what that tells you about the interior of the planet and its thermal history and when it began to contract, or when it was hot enough on the inside to produce this voluminous amount of lava that comes to the surface. The other thing it starts to tell us is maybe what will Mars and Venus and Earth perhaps one day come to resemble, right?
Right.
Notwithstanding the sun eating Earth and Venus and Mercury in the next few billion years. But you know, if you roll the clock forward enough, if I'm right, inevitably, first Mars and then Venus and then Earth will eventually cease to have widespread volcanism as they run out of thermal energy. Now, to be fair, this may not happen before the sun eats us, right? But if you know, there are probably planets, we know there are some exosolar planets, and I'm going to come back to those in a moment. Some exosolar planets, at least we know of one that's 11 billion years old, right? It's stable, it's around a red dwarf star. Imagine an 11 billion year old planet, right? The planets in our solar system are 4.5 billion years. What does an 11 billion year old rocky planet look like? Well, maybe it looks a bit like Mercury and the Moon.
Yeah.
Maybe you run, and even no matter how big you are, you run out of heat energy, you start to contract, you start to localize your volcanic material in places where the crust is weak, which in Earth's case won't be impact basins, because all the really big basins are long since gone, but it will be where the crust is weak today. It could be those continental rift zones. It could be the spreading centers, right? Eventually plate tectonics will stop, but you'll still have these big weaknesses in the crust, and that's probably where the last gasps of volcanism will be. You'll stop making huge volcanoes, right? And eventually, you may still produce melt, you may still produce magma, but it won't be able to reach the surface because the entire surface is in compression. That's the idea. And the reason this is important is not just because perhaps it tells us what the future of Earth or Venus or Mars will look like, but maybe the fate of volcanic worlds in general. Right? We're talking about ever increasing number of exosolar planets, and those planets that orbit stars that aren't our own. And we're getting better and better, and we are making more of an effort to focus on the Earth-size or smaller rocky ones. Right? We are biased to detecting those worlds that are very close to their suns and that are very big. But we are getting better at detecting smaller ones. And the holy grail of exosolar planetary science really is: can we find an Earth? Right? Can we find a second? That's exactly it. That's one thing we really want to know. And so our question is, what kinds of predictions, if any, can we make in terms of where we should be looking? Where should we point our telescopes, particularly the more developed stuff in the future, right? You know, the more advanced worlds that are really focused, like James Webb, and even the telescopes that will follow a generation after Webb. And if we can draw those inferences from what we see in our solar system, if we can make those generalizations, then the kinds of worlds we need to be looking at are all the worlds that are relatively young around a relatively young star. Now, it's very hard to work out the age of a particular star. If it happens to be in a globular cluster, you can make some effort, you can draw some inferences there about the ages of stars based on its color. And then reasonably, I think it's a defensible thing to say, if the star is 5 billion years old, well, then its planets are probably the same age. So finding a star that might be 1 or 2 billion years old and finding that it has rocky planets, even the relatively small ones there, they're probably volcanic. If they have an atmosphere, you could look to see if you can measure using transit photometry or transit spectrometry. Can you say anything about the composition of the atmosphere? Can you, if you observe this world over several months or several years, do you see changes in gases that we know are volcanic on Earth? Right, that's something you can look at. Or if you find a planetary system that's 8 billion years old, I'm making this number up, and we don't know for sure if it's 4.5 billion years gets you on Earth. We don't know that, right? Because it depends on what the heat-producing element abundances are of these stars and their planets. But if you find a planetary system that's 8 billion years old, well then it's a good guess that the smaller rocky worlds there are going to look like Mercury and are going to look like the Moon. And they're not good places to train your telescope. And the more potentially likely candidates for ongoing volcanic activity are going to be those worlds that are bigger, either around young stars or the bigger worlds like Earth size and perhaps even bigger around older stars. Right? That's the idea. If it comes to pass in the next 15 or 20 years that we see evidence for active volcanism, maybe we see a thermal anomaly on the night side of the world, or we see in its atmosphere volcanic gases and it's Mercury sized and it's 8 billion years old, well then this is wrong and we can't extrapolate. But that's still a result. That's still something we didn't know. But if we look at the worlds in the inner solar system, I think we can at least get a sense of what the rules are that govern volcanic worlds and the fates of volcanic worlds in general. And that's the idea behind this article.
Cool. Yeah, and going forward, well, hey, number one, thank you for sharing that, Paul. That was awesome. And yeah, just looking forward, right? I mean, sort of the era of discovering yet another exoplanet is kind of behind us now. right? There's thousands of them. You don't write a paper about the discovery of a single exoplanet unless it's a really special one, Earth 2.
Right.
And so sort of where the future goes, at least in exoplanets, is characterizing their atmospheres and characterizing their surfaces.
Right.
And there's a lot of activity in that. And that's not to diss our own solar system. There's still a lot to learn about our own solar system. So if you look in your crystal ball for our solar system, do you see forthcoming NASA missions that would be of use for studying their surface geography?
Absolutely, yeah. There's a bunch of things that I think we could do. So right now, in terms of what's actually coming down the line, there are right now. So you might know that there's NASA's running one of what's called its Discovery mission competition right now. NASA has a variety of different planetary missions, and in terms of scale, and scale here means money. Discovery missions are about a little bit under $500 million, which is not much for a planetary mission. Is a huge amount of money in an absolute sense. There are 4 missions that were announced in February that are under what's called down selection, where they give them an extra year or so to develop a more detailed concept study. 2 of those 4 missions are Venus-focused missions.
Okay.
So NASA has not flown a mission since '89, so to Venus. So I am psyched that one of them may be picked.
Are you part of one of the teams?
I am not a part. I had been involved early in another concept that didn't ultimately make its way to proposal, but I am loudly cheering on both. The other 2 were Io. Actually, let me step out for a second and say, by the way, Io does not feature in this conversation because Io's volcanism is driven by tidal friction, tidal heating. Here, I'm talking only about those worlds where the majority of volcanic activity is being driven by the heat they have inside from radiogenic elements. The first places where we're really going to see evidence for ongoing rocky volcanism in extrasolar planets are probably going to be worlds where the tidal forcing is what's doing it.
Fair enough.
And they're interesting, they're cool, and Io is a very, very interesting exploration target, but really what drives me are those worlds that have their own internal heat energy. You could transport Earth into deep, deep space and it will continue to be volcanic. Yeah, whereas if you take Io and you move it away from Jupiter,
it'll cool off pretty quick.
But 2 of those missions, one is called Veritas, and Veritas would fly a high-resolution radar that would give us, right now, radar image data, it is image data, but it's from radar. For Venus is about the same as Viking we had for Mars, right? And Viking told us a lot of Mars, but boy, we have learned some new exciting stuff in the last 15 years with the really high-res stuff, right, for Mars. Cool. Imagine what we'll learn for Venus with high-res. And one of the things that high-res images and topography might give us for Venus are what is the nature of the older stuff? Are the craters we've missed? What's the kind of, what kind of contacts do we see? Can we see anything with timing? And even spectral, there are chemical data you could measure from orbit of Venus that we don't have right now. So there's a lot of low-hanging fruit for Venus in terms of morphology and timing and chemistry that I'm hoping that Veritas won't answer all the questions, but we'll get at those questions. The other Venus mission is called Da Vinci Plus, and Da Vinci Plus will be an entry probe that would come through the atmosphere. There are some absolutely key measurements we do not have that we need from the middle Venus atmosphere, kind of where I am here, that if we measured, even one measurement would already help us to begin to put bounds on models for the interior history and chemistry of Venus, including the implications it would have for volcanism, right? So there's some pretty important stuff. Now, I don't know if either will be picked or both. Certainly either mission would seriously advance our understanding of Venus, which is, I think, there's a lot of bits missing in the puzzle right now, but the single biggest chunk that's missing, I think, is Venus. But we have the planetary decadal, which is coming up now, the Planetary Science and Astrobiology Decadal. Yep. The National Academy is running on behalf of NASA. That's going to start later this year for this period 23 through 2032. And one of the things we're going to be asking in the decadal survey is, what are our priorities going forward? And I was involved with a team out of Johns Hopkins Applied Physics Lab, who we've done a study about what a Mercury lander would do. And how much money and what kind of energy and technology would it take to land on Mercury? And spoiler, it's really hard to do. But if we were to land on Mercury and we could get in situ chemistry of the rocks on Mercury, that would tell us a lot about its interior composition and its history of volcanism, particularly the part that's no longer preserved from the surface. Like, the oldest preserved part of Mercury is 4.1 billion years old, but the planet's 4.5. So what's the earlier 400 million years? We don't know. Similar questions from Mars.
Not only do you want to land on Mercury, you need some sort of a rover, right? You want to be able to putz around this a little bit.
If we could, yeah, and suddenly our mission goes from 1 to 4 billion. I mean, unfortunately, this is the issue with these things, right? The technology required. I mean, ultimately, I'd love to see a rover rove across Venus, but we're not going to be able to do that until we have high temperature electronics, which there are some really smart folks at NASA Glenn working on that technology today. But we're probably 10 or 20 years realistically from seeing a rover on Venus. But we'll get there, and being able to have there, a rover there for months listening. In fact, a really interesting aspect of Venus is that, so you may know that if we have a big earthquake on Earth, for example, we know that there are surface waves, there are body waves, there are seismic waves that travel from the earthquake, and we can detect them across the planet depending on how big the quake is. Okay. But there is an amount of coupling between the ground and the air. And you can fly a balloon, for example, and you can use infrasonics, and you can actually listen to quakes, because that seismic energy actually travels with the air as well. That coupling on Venus is 60 times stronger than it is on Earth. So one of the ways you could listen for earthquakes on Venus is in a balloon.
Very cool.
But one of the ways you get seismic energy is not just earthquakes, volcanoes produce them.
Yep.
So you could even listen for volcanism on Venus as well, right?
Very cool.
Exactly, this pops. So there's lots of ways we could try and answer these questions. Continued exploration of the solar system is going to be key. What's the history of the really ancient volcanism on the moon? Did the moon have a period of volcanism? What's underneath the plains of the Mare that we see? There are these things on the moon called cryptomare, and they sound exactly the same. They're cryptic mare. We don't quite know when they're in place or what they're made of, and there are concepts to go and visit those deposits and work out how old they are and what they're made of. Just even fundamentally, Earth. What's the history of volcanism on Earth? How far back can we trace volcanism? Where's the evidence for plate tectonics in Earth's geological history? Those basic questions all tie into what is the history of volcanism on a world in general? What's it like when it starts? One of the things that I think is something, my hunch that we'll end up showing, I'm hoping in the next few decades, is, remember we talked about that part of Mercury, Borealis Planitia, that did 6% on the surface? Right. That is one of what we call these smooth plains, right? And like I said at the beginning, smooth plains are so called because they are relatively smooth. They are relatively not heavily cratered. Borealis Planitia is around 3.8 billion years old. It's super old. But it's relatively smooth because the cratering flux just took a nosedive, right? So even something that old doesn't have that many craters on it. But I mentioned in passing that most of the surface, right, 75% of the surface of Mercury is not smooth. But my guess is, and I know the researchers have this view too, most of that material is probably formerly smooth plains, and sustained impact bombardment just made it not smooth. But my guess is Mercury was originally all smooth plains. Yeah. And my guess is Borealis Planitia, 6% of the planet's surface, is the last example of that kind of resurfacing. But my guess is that the crust of Mercury is made up of 60 or 70 or 100 of such huge outpourings of lava. And if that's the case, if that's true, with the exception maybe of the moon, because the moon formed in a slightly different way, we may come to find that Mars and Venus and Earth may have been characterized very early on by biblical proportions of lava pouring onto the surface, particularly as short-lived radiogenic elements were producing unbelievable amounts of heat. If that's the case, we may then find in the future a very, very young, a newborn rocky planet. The entire thing may be glowing, not from what we call the magma ocean phase, which is the very earliest stages of a world when everything is molten. But once that phase is over, and volcanism in the sense we have it today is where the inside gets melted and reaches the surface, once that process is underway, it may be that for the first couple of 100 million years of a planetary body, you have unbelievable amounts of volcanism pouring out on the surface. Cool. So that's one of the questions I have, and I think exoplanets really might offer us an opportunity to kind of test that idea too. So that's where I think, if I look at my crystal ball, I think in the next 10, 20, 30 years, we'll get a better idea of what the whole lifetime is of a volcanic world, the fate, if you like, of volcanic worlds.
Cool. The future is bright for planetary geology. Awesome. Paul, I want to thank you so much for sharing your article and chatting in depth about planetary geology.
My pleasure. Thank you for your interest. It was fun.
All right, everyone. Thank you so much. And we're gonna continue this series in Sky and Telescope. And in fact, in the next one, we're going to be covering ice volcanoes, and we'll have Rosalie Lopez on talking about that. So, thank you, Paul. Bye-bye. Bye, everyone.
Thanks, folks. Take care.